Welcome to this EWRB Electrical Service Technician Training course. I'm Aria, an electrical tutor working with Whitroy. In this course, I'll guide you through all the topics covered in the EWRB Electrical Service Technician Exam Teaching Guidelines. Welcome back. In our last lesson, we talked about electrical safety, personal, and how electric current affects the body. Now we'll look at how we can protect ourselves using personal protection devices. These devices are designed to protect people, not just wiring. Fuses and circuit breakers protect equipment, but they don't stop small leakage currents that can harm you. That's where residual current devices and isolating transformers come in. They detect faults or isolate the supply to prevent electric shock. Let's start with residual current devices, or RCDs, and see how they keep us safe. Let's begin with Topic A. Topic A. Purpose of RCDs. RCDs provide supplementary protection to users of electrical appliances and equipment. They are not designed to replace fuses or circuit breakers; those protect the wiring. Instead, RCDs protect people by disconnecting the circuit when even a small current leaks to earth. Think of it this way: if someone touches a live conductor while standing on the ground, a few tens of milliamps can flow through their body. The RCD senses this imbalance between the active and neutral conductors and trips in milliseconds, cutting off the supply before serious injury occurs. Topic B. Tripping current and operating times. Regulation 20. Under Regulation 20 of the Electricity Safety Regulations 2010, an RCD used for personal protection must trip at no more than 30 milliamps and operate within 300 milliseconds. Some special RCDs trip faster or at lower current levels. 10 milliamp RCDs are used where there's a higher risk, such as in childcare centers or medical rooms. These timing and current limits are tested to make sure the RCD will protect the user before an electric shock becomes harmful. Topic C. Type of RCD required in New Zealand. In New Zealand, all RCDs installed for shock protection must be Type A as specified in S/NZS 3190 and S/NZS 3000 Clause 2.6.1. Type A RCDs detect both pure AC fault currents and pulsating DC currents, which can occur from electronic loads like washing machines or LED drivers. Older Type AC RCDs only detect pure AC and are no longer acceptable for personal protection in new installations. So, when fitting or testing RCDs, always check the label; it must show Type A. Topic D. Operating principle of an RCD. Let's now talk about how an RCD actually works. Inside the RCD there's a small current transformer with both the active and neutral conductors passing through it. Under normal conditions, the current going out on the active equals the current returning on the neutral. The magnetic fields cancel each other, and the RCD stays on. If any current leaks to earth, say through a faulty appliance or a person, the balance is lost. That imbalance induces a voltage in the sensing coil, which triggers a relay to open the contacts and disconnect the circuit. It all happens in a fraction of a second. You can think of it as a difference detector that constantly compares what goes out with what comes back. Topic E. Different types of RCDs. Now let's move to Topic E. The different types of RCDs you'll encounter. There are several, each with slightly different purposes. 1. RCCB, Residual Current Circuit Breaker, provides earth leakage protection only. It doesn't include overcurrent protection, so it must be used with a circuit breaker or fuse. 2. RCBO, Residual Current Circuit Breaker with Overcurrent Protection, combines both RCD and MCB functions in one device. It trips on both earth fault and overcurrent, common in modern switchboards. 3. SRCD, Socket Residual Current Device, a socket outlet with a built-in RCD. It gives portable protection for specific outlets. 4. PRCD, Portable Residual Current Device, a plug-in RCD used on portable equipment, for example, on construction sites or with outdoor tools. We also classify RCDs by how they are powered. Functionally independent of line voltage, they trip using energy from the fault current itself. Functionally dependent on line or auxiliary voltage, they rely on the mains or battery power, often used in portable types. Typical ratings are 10 mA or 30 mA for personal protection, and industrial types may be higher for equipment protection. And finally, RCDs can be classified by DC component sensitivity, Type A, Type F, or Type B, depending on whether they detect pure AC, pulsating DC, or smooth DC fault currents. Topic F. RCDs and protection in S/NZS 3000. Under S/NZS 3000 Section 2.6, RCDs are part of the requirements for protection against electric shock. They provide supplementary protection in addition to basic insulation, barriers, and equipotential bonding. In damp or wet areas, RCDs are often the last line of defense when a person accidentally contacts live parts. That's why every socket outlet rated less than or equal to 20 amps must be RCD protected at 30 mA. Lighting and fan circuits in bathrooms must also be RCD protected. So remember the spoken rule. Water, people, and electricity never mix, so RCDs are always required. Topic G. RCDs for handheld appliances. Now for Topic G. RCDs used with handheld appliances. Handheld tools like drills, grinders, and extension leads are high risk because the user's body completes the path to Earth. Portable RCDs, PRCDs, are used for this reason. When plugged between the supply and the tool, the RCD trips instantly if any current leaks through the user. For example, a PRCD plugged into a portable lead on a building site must trip within 300 milliseconds at 30 mA, or faster if 10 mA rated. Topic H. 10 mA RCDs for special areas. Now let's discuss 10 mA RCDs. According to AS/NZS 3000 Clause 2.6.1, 10 mA RCDs are required in areas of increased risk, for instance, rooms used by children, medical or laboratory areas, and places where people may be in contact with water and earth metal at the same time. The lower trip current provides extra protection because young people and patients are more sensitive to electric shock. Topic I. Testing RCDs. Practical procedure. Now let's finish the RCD section with testing. RCDs must be tested to confirm compliance with Regulation 20 and AS/NZS 3017 procedures. Here's how we do it in spoken step-by-step form. 1. Isolate the circuit and ensure you can test safely. 2. Visually inspect, make sure there's no damage, the label shows Type A, and the test button is accessible. 3. Press the test button on the RCD. This creates a small earth leakage current and should cause the device to trip immediately. If it doesn't trip, the RCD is unsafe and must be replaced. 4. For verification, use an RCD tester or insulation tester with RCD mode. Apply a half times, 1 times, and 5 times rated current test to check that tripping times meet the standard. At 1 times I delta N, 30 mA, it must trip within 300 milliseconds, at 5 times I delta N, within 40 ms. 5. Record the test results on the test sheet and label the circuit as RCD tested, compliant. Always perform tests on all RCDs during commissioning, periodic verification, and after any alteration to the circuit. Applied example, RCD in use. Imagine you're on a site and using a 230-volt grinder through a PRCD lead. You press the test button before work, it trips. After resetting, you start grinding, and accidentally the lead touches a wet surface. Instantly, the RCD trips, cutting power before you even realize what happened. That's how RCDs save lives every day. Summary of RCD. So, let's summarize the RCD part before we move to isolating transformers. RCDs provide supplementary shock protection, trip at less than or equal to 30 mA within 300 milliseconds, Reg 20, must be Type A for new installations, are available as RCCB, RCBO, SRCD, and PRCD, are mandatory for sockets less than or equal to 20A and all damp or high-risk areas, and must be tested regularly with the test button and an RCD tester. In short spoken form, RCDs protect people, not wires. Test them often, trust them always. Topic J. Basic principle of isolating transformers. Now let's move briefly to isolating transformers, which also provide personal protection but in a different way. Topic J. Basic principle. An isolating transformer has separate primary and secondary windings with no direct electrical connection between them. This isolation prevents a user from receiving a shock because there's no return path to earth from the secondary side. Topic K2N. Safe use in earthing. Maximum safety is achieved when only one appliance is connected to the transformer's secondary. If multiple appliances are connected, their earth conductors must be bonded together at the transformer but not earth, so there's still no path to earth through the body. In some situations, isolating transformers are used together with other safeguards like RCDs or extra low voltage systems for additional protection. Topic N. Transformers rated in kVAR. Finally, isolating transformers are rated in kVAR, kilovolt amperes, not watts, because their output depends on both voltage and current regardless of power factor. The kVAR rating shows the maximum apparent power the transformer can safely deliver. Summary of isolating transformers. In summary, an isolating transformer protects by separating you from the supply. Use one appliance only, keep the earths bonded but floating, and always match the kVAR rating to the load. Bringing it all together. That completes Topic 8.13, Personal Protection Devices. We've spent most of our time on RCDs, their purpose, operation, types, testing, and standards, and we finished with isolating transformers as another means of personal protection. Remember this spoken checklist. Detect, disconnect, test, and isolate. RCDs detect and disconnect, transformers isolate and protect. That's the end of Topic 8.13, Personal Protection Devices. In our next lesson, we'll move on to Topic 8.14, Safety Tagging System, where we'll learn how tagging and identification procedures help control electrical hazards during maintenance and service work.